Nuclear fusion is a process by which two atomic nuclei combine to form a single, heavier nucleus, releasing vast amounts of energy in the process. This process is the fundamental source of energy for stars, including our Sun, and has the potential to provide a nearly limitless, clean energy source for humanity. Understanding nuclear fusion requires exploring its physical principles, the history of its discovery, the conditions under which it occurs, its applications, and the challenges involved in harnessing it for practical use. Nuclear fusion is the opposite of nuclear fission. In fission, heavy atomic nuclei split into smaller nuclei, releasing energy, while in fusion, light atomic nuclei combine to form a heavier nucleus, also releasing energy. The process typically involves isotopes of hydrogen, the simplest element, as they have low atomic numbers and can easily fuse under extreme conditions. The most common fusion reactions involve isotopes of hydrogen. Deuterium, a hydrogen isotope with 1 proton and 1 neutron, and tritium, a hydrogen isotope with 1 proton and 2 neutrons. When two deuterium nuclei, or a deuterium and a tritium nucleus, collide under high temperature and pressure, they can fuse to form a helium nucleus, releasing a neutron and a large amount of energy. The most common fusion reaction in stars, including the Sun, is the deuterium-tritium fusion reaction, where deuterium and tritium fuse to create a helium nucleus, a high-energy neutron, and 17.6 million electron volts of energy. Nuclear fusion is the process that powers the Sun and other stars. Inside a star, the immense gravitational pressure and high temperatures create the necessary conditions for fusion. In the Sun's core, the temperature is about 15 million degrees Celsius, and the pressure is around 250 billion atmospheres. At these extreme temperatures, hydrogen nuclei move at such high speeds that they overcome their electrostatic repulsion and collide with enough force to undergo fusion. The energy released in these fusion reactions radiates outward from the core and provides the heat and light that we receive on Earth. The energy released during nuclear fusion comes from the difference in mass between the reactants and the products. This is described by Einstein's famous equation, which shows that a small amount of mass is converted into a large amount of energy. In a fusion reaction, the mass of the resulting helium nucleus and the released neutron is slightly less than the mass of the original deuterium and tritium nuclei. This mass defect is what is converted into energy. The energy released in nuclear fusion is orders of magnitude greater than that released in chemical reactions like combustion. The idea of nuclear fusion has been known for over a century, but practical research into harnessing fusion energy began in the mid-20th century. Key milestones in fusion research include the idea that stars generate energy through nuclear reactions, first suggested by British astrophysicist Arthur Eddington in the 1920s. The discovery of the neutron by James Chadwick in 1932 and the theoretical work of Hans Bethe and others helped establish the understanding of nuclear reactions in stars in the 1930s. The development of controlled nuclear fusion became a major goal for scientists in the 1950s, with early attempts focusing on using magnetic fields to confine hot plasma, leading to the creation of devices like the tokamak and the stellarator. The first major experimental fusion reactors, including the tokamak design in the Soviet Union and the fusion research in the United States, were built in the 1960s. The development of advanced fusion technologies, such as inertial confinement fusion using lasers, and the creation of more efficient and larger tokamaks, occurred in the 1980s and 1990s. Significant progress in fusion energy research has been made in the 2000s with projects like ITER and advancements in laser-driven fusion at facilities like the National Ignition Facility. For fusion to occur, 3 conditions must be met. High temperature. The nuclei must have enough kinetic energy to overcome their electrostatic repulsion. This requires temperatures in the millions of degrees, similar to the core of stars. High pressure. High pressure helps bring the nuclei close enough for fusion to take place. In stars, this is achieved by the immense gravitational force of the star's mass. On Earth, this can be achieved in controlled fusion reactors. Confinement time. The particles must remain at the high temperature and pressure long enough for fusion to occur. This is a significant challenge for fusion energy research, as maintaining these extreme conditions requires advanced technologies. There are two primary approaches being explored for achieving controlled nuclear fusion on Earth: magnetic confinement fusion, MCF, and inertial confinement fusion, ICF. Magnetic confinement fusion is the most widely studied method for achieving nuclear fusion. It uses powerful magnetic fields to confine a hot plasma and prevent it from touching the walls of the reactor. The two main types of magnetic confinement devices are tokamak and stellarator. A tokamak is a donut-shaped device in which plasma is confined by magnetic fields and heated to the necessary temperature for fusion. ITER, currently under construction in France, is the largest and most advanced tokamak in the world. A stellarator is a more complex magnetic confinement design that uses twisted magnetic fields to stabilize the plasma. Stellarators are being researched at institutions like the Wendelstein 7X in Germany. Inertial confinement fusion involves compressing a small pellet of fusion fuel using powerful lasers or other forms of energy. The goal is to achieve the extreme temperatures and pressures needed for fusion. This method is being researched at facilities like the National Ignition Facility in the United States. Nuclear fusion offers several potential advantages over traditional energy sources, such as fossil fuels and nuclear fission. Fusion reactions produce no greenhouse gases or long-lived radioactive waste, making them an environmentally friendly alternative to fossil fuel-based energy. The primary fuel for fusion, deuterium, is abundant in seawater, and tritium can be bred from lithium, making fusion a potentially sustainable energy source. Unlike fission reactors, which can experience catastrophic failures like meltdowns, fusion reactions do not pose the same risks. If a fusion reactor fails, the reaction simply stops. Fusion produces much more energy per unit of fuel than chemical reactions or fission, potentially providing a nearly limitless supply of energy. Despite its potential, nuclear fusion faces significant technical challenges. The conditions needed for fusion are difficult to achieve and maintain. Current experimental reactors require massive amounts of energy to heat the plasma to the required temperatures. Maintaining the stability of the plasma and preventing it from touching the walls of the reactor is a major challenge in magnetic confinement fusion. Tritium is not naturally abundant, so it must either be bred in the reactor or sourced from limited stocks. Achieving a net positive energy output has not yet been demonstrated in a practical fusion reactor. ITER aims to achieve this milestone. Fusion reactors require significant investment in research and infrastructure, and the long time frames for development make it a costly endeavor. The future of nuclear fusion looks promising, but it will likely take several more decades before it becomes a practical and widespread energy source. Ongoing research efforts, particularly at ITER and other international fusion projects, are focused on demonstrating sustained fusion reactions and achieving energy break-even. If successful, nuclear fusion could revolutionize the global energy landscape, providing a clean, sustainable, and virtually inexhaustible source of power. Nuclear fusion is a fundamental process that powers the stars, and harnessing it on Earth could solve many of the world's energy challenges. While substantial progress has been made in the field, significant technological, economic, and engineering challenges remain. However, with continued investment and research, nuclear fusion holds the potential to transform the global energy system, providing a clean and abundant source of energy for future generations.